welcome to Simcast, a podcast brought to you by the Society for Imaging, Informatics, and Medicine. Greetings, Simcasters. In this episode, host Mohanad and guests Jason Klotzer and Dr. Markus Herrmann take us on a journey through the world of digital pathology. It's always interesting to see how one field, when faced with adopting technologies used in a similar field, faces certain questions of whether to reuse what has already been done, completely scrap and start fresh, or take best-of-breed solutions and combined with insights gained over decades of experience, come up with a robust system that takes into account workflows as well as new and exciting technologies and standards. The adoption of overlapping technology standards vis-a-vis DICOM by the digital pathology community has led to exciting insights and innovations that are discussed today. Indeed, the digital pathology community is actively engaged in the imaging healthcare enterprise and making full use of new toolkits to advance the reach of the pathologist. The conversation also covers, with great enthusiasm, a hackathon sponsored by the Digital Pathology Association and the DICOM Working Group 26 for Pathology. We hope you enjoy this episode.
Thank you, Markus and Jason, for joining us today. So we start with DICOM. So we know DICOM is a flexible standard, and pathology workflow is going to be a little different, where maybe DICOM wasn't necessarily built to deal with those kind of workflows and nuances. Were you considering any other standards before you settled on DICOM? And if you did, why weren't they chosen? Did you even think about maybe creating your own DICOM standard, like PathCom or something along those lines?
Excellent question. And I think it's a question that often comes up that a lot of people ask, what are the benefits of DICOM? Should we consider something else? Maybe to begin with, I just want to clarify that DICOM is a standard for imaging. So of course, in pathology, there are many other modalities than, whole slide imaging or microscopy imaging in general. So of course, other standards are required for different types of data, and all of the information about specimen and so forth is not necessarily stored primarily in DICOM. When it comes to the imaging, though, there are several information that we need from the laboratory that we would like to link with the images. And DICOM is really unique in that aspect of having metadata fields in files or data sets that can be communicated so that you can communicate the imaging data, basically the pixel data, together with relevant contextual metadata. For example, the identifier of the patient or the identifier of the specimen that was actually imaged, as well as some other descriptive metadata about how the specimen was fixed, how it was embedded, what stain was used to enhance contrast in the image, and so forth. So there are other standards out there for encoding image information. If you just have a simple image, you could use a JPEG. If you have multiple images, you can combine them into container formats like TIFF. And DICOM is very similar to these container formats. So a TIFF file, for example, is closely related to a DICOM file. It just uses a slightly different syntax. And so you could, in principle, encode all of that information in any other file, like a TIFF file, and just use similar attributes to describe the clinical metadata or other contextual information. But the point is really that DICOM already exists in that respect and has been used in radiology for quite a long time. And a lot of things that you may not necessarily consider in the first place when designing your own standard have already been considered, have been battle tested in practice for many years. And so this is basically why we've chosen DICOM to begin with. I've personally been down other paths and encoded information in a variety of proprietary formats myself, and burnt myself a few times along the way. So I think I've learned my lesson and then went with an existing standard rather than trying to create my own, which can be a bit of a rabbit hole. I don't know, Jason, what are your thoughts on this?
Yeah, so similarly, I would say radiology, having adopted DICOM many years ago, has built a very deep tool chain very deep sort of workflow expectations and built a lot of tooling around that. Digital pathology having a lot of its own sort of nuances with respect to the kind of metadata that gets stored. I would say that that's kind of the gap that DICOM had to support via DICOM WSI. So it wasn't exactly a perfect match immediately, but considering there were so many similarities with respect to at least imaging transfer syntax support, imaging visualization, at least at the tile level, DICOM did have to add some other nuances with respect to the pyramid type encoding, but a lot of the other sort of toolchain aspects and even metadata aspects already being in place and having many, many years of, hardening, I would say, I think it's really the best approach. I mean, you could say the same thing for other industries, looking at dermatology, ophthalmology, dentistry even. There are specific nuances in the clinical care path around imaging, but reinventing everything, I think is just, it's daunting. So yeah, I am 100% a proponent of the DICOM first approach when it comes to medical imaging formats and work. Yes.
Maybe just to add to this, the metadata is really the part that I'd like to emphasize here, because the pixel data itself is usually rather trivial and there are existing formats. And like I said before, DICOM is just a container format. So it can contain JPEG blobs, for example. So that part is rather easy. But describing what is in the pixel data and how that basically relates to the real world objects, meaning the patients or the specimens and studies or cases and so forth, that's the tricky part. And that's also something where we want to include that information and link it to the imaging data so that we can interpret it in context later on. But at the same time, we want to be able to de-identify that data for research, for example. This is one great example where DICOM provides confidentiality profiles that allow you to then de-identify the metadata again and strip out anything that may be considered PHI. And these are all of these things that you wouldn't necessarily think about initially when you create your own standard. You basically focus on a few subsets of those and then realize that you need to add all of these things on top. And in my experience, what happens if you start with a new thing, you end up with something that is basically very much like DICOM, just different enough to not be interoperable. And that's the part that we wanted to avoid.
Thank you both. That's a very thoughtful answer. So you've talked about all the things that DICOM brought to the table, that it's a container, it comes with anonymization, standards and profiles. So tell me about the things that didn't necessarily just work out of the box, things that you had to adapt. For example, I've heard about, the frame attribute being adapted for digital pathology to work like a pyramid approach. Can you, gentlemen, explain a little bit more about that?
I think Jason already touched upon some of these things. There are two so-called supplements that were added to the DICOM standard that added functionality that was necessary to support digital pathology. The first one was what was called Supplement 145, which introduced this concept of a pyramid. Although it's not actually explicitly defined in the standard, it allows you to encode images that are very large in like 2 dimensions, so large grids, and tile them, basically chunk them into smaller parts that can then be compressed separately and can also be accessed individually. And that is very similar to TIFF, where you can have individual tiles in there, and you would basically have byte offsets to these individual tiles so that you can read these, smaller parts of an image very efficiently. So that was one thing that was introduced into the DICOM standard, and it was necessary to allow these, multi-scale representations of images that were important for viewing applications, similar to like Google Maps, where you basically zoom in and then the individual tiles would trickle in. Another aspect that was important that got added a little bit later was Supplement 122, which introduced attributes to describe specimens. And I think that is maybe one of the biggest differences between radiology and pathology, because the imaging target in pathology is generally not the patient, but it is a surgical specimen that was derived from the patient. And so now you need to have just identifiers to identify that specimen and the slide or the container in which the specimen is contained and being imaged in. But you also have things now, you need a different coordinate system. So it's no longer the patient coordinate system, but the slide coordinate system, for example. You may want to describe how that specimen was derived from the patient in the first place. Like, was it collected through a biopsy or surgical resection? Was it fixed with formalin, or is this a frozen sample, and so forth? And so a lot of additional attributes and mechanisms were introduced into the standard to describe the specimen and the whole specimen preparation process in quite some detail. And I think so that is probably the major difference between radiology and pathology. There are some differences in how pixel data is being represented and the size of the pixel data and so forth. But the fact that we don't image necessarily the patient in pathology, but a specimen that was derived from the patient, and that this specimen gets heavily processed in the laboratory. We section it, we fix it, we stain it, and so forth. And all of these details may be important, for example, for a display system or an image analysis system down the line. So we want to capture that information and encode it together with the pixel data so that a downstream application could utilize the info.
Yeah, so just building on what Markus said, and I'm not going to go into the specific attributes as he very, very cleanly described them. I think from a sort of viewer consumption standpoint, digital pathology has introduced a sort of new rendering paradigm, which is the pyramid sort of rendering paradigm. I mean, you look at sort of the, I don't want to say classic, but the traditional modalities, that a viewer would need to render. And you have your sort of 3D volumetric ones, MR, CT, those sort. You have your sort of time-based, which would be, ultrasound, for your cines, or maybe X-ray angiography. But those are all really just single sort of slice, and in some cases, single slice bioreconstruction views of imaging data. Whereas pathology introduced a sort of large scale, being able to turn a 20,000 or more by 20,000 single view of a slide that has been digitized into something that's representable in a single sort of viewport within the viewer. And that's where your whole pyramid approach comes in, which is kind of a new paradigm for a lot of viewers to be able to implement in an efficient kind of way. So I think that paradigm is also very different. Well, the standard did have to adopt it from a paradigm standpoint, but from a metadata standpoint, I think a lot of the requirements were in place already, just the encompassing paradigm had to be adopted from that standpoint.
Excellent, thank you. So speaking of standards, and maybe just drifting away from technical standards like DICOM, I'm curious, for a lot of our listeners who are familiar with radiology, there are standards for brightness of monitor display, resolution, the background light in a room, so on and so forth. How do these things translate to in digital pathology?
Yeah, great question. There is also a major difference between radiology and pathology that we didn't get into so far. I mean, we've talked about the pyramid representation versus 3D representation and the different approaches for rendering, and the fact that the imaging target is the specimen rather than the patient. But in at least current practice, in whole slide imaging, we're primarily dealing with color images, which is also quite different from radiology, where most of the images are grayscale images. But what you referred to here, the fact that we actually need to adjust a lot of the pixel values in order to display them to humans so that they can interpret them in a correct way, is something that also translates to pathology, just slightly different because we're dealing with color rather than grayscale. And so there are existing standards, both in radiology and pathology, that have been incorporated into DICOM, right? So the grayscale standard display function, for example, is something that takes a whole part 14 in the DICOM standard, that describes how these grayscale, these values, when they are stored in the DICOM dataset, how they need to be transformed so that you ultimately get a perceptually uniform or linear grayscale state. And so there are all these complexities around that. If you consider, for example, a CT image where the data may be stored as unsigned integers in the file because you can then compress it with a certain JPEG codec, for example, but then you actually need to transform them into Hounsfield units, and then you may need to window them, for example, for the bone window or the lung window. And so you only take a certain range of values, and then you want to map them into something that when a human looks at it on a monitor, actually interprets these values correctly. And it turns out that human vision is quite tricky in that respect. So for example, if we just look at grayscale values, we know that humans basically have a much harder time seeing differences in intensity in darker areas of the image versus brighter areas in the image. So there is this Grayscale standard display function that was incorporated into DICOM, so that you need to use to adjust your monitors and so forth, that when Grayscale values are displayed to humans, they interpret them correctly and don't get misled by their own vision system, so that certain areas of the image would be interpreted differently because they have a different intensity value. And so that is not necessarily directly applicable to pathology, where most of the images, at least for now, are color. But there are different problems in color that are very similar, I think, conceptually. So there we also know that humans perceive different colors differently. And there are also all these problems that if, for example, a scanner would have acquired images in a certain color space and compressed them into, JPEG or something, and then you display them on a different monitor with a different color space, a lot of things can go wrong. And so this is where DICOM has also incorporated another standard, so an external standard called ICC from the International Color Consortium, that provides so-called profiles that allow you to take an image that is defined in one color space, in the source color space, transform it into a reference space, and then basically transform it into another target space. So you may, for example, have an image that gets acquired as in RGB space on a scanner, but then you want to display it in like CMYK space on a monitor and so forth. So these ICC profiles would now provide you these lookup tables or mappings to first transform it into a device-independent reference space, and then transform it into your space that your display supports. And so you have the same effect similar to what you know in radiology as the Grayscale standard display function. Similar concepts need to be applied to color data so that you get ultimately a perceptually uniform or device-independent color image that people can then interpret reliably.
Yeah, I absolutely want to add to this one because I've also seen various usages of ICC profile, for instance. The general mapping of the concept that was adopted in radiology for the Grayscale standard display function, GCSDF. I do believe there are proposals around, the color standard display function as well. Having worked in this industry with vendors, from the hardware side as well, I know that, usually the adoption of these sort of standards really have to be full stack, with respect to first saying, okay, well, the acquisition needs to be able to know how to map between these values. You also have the ICC profile, which I'm going to get to in a second. Then getting down to the point where it's going to actually be visualized on a specific monitor, like, for instance, I can say I know Barco, Totoku, these sort of large monitor vendors, they have the sort of calibration built into them using the GCSDF, for instance, for Grayscale, and hopefully sometime in the near future, CSDF as well. I think the whole stack needs to be aware of it for the most accuracy. I think, quite honestly, it's also an evolutionary type thing. Like, for instance, I think ICC profile and finding the most accurate visual color representation is the right direction from a color standpoint. But what I've seen in practice from ICC profile in some cases is that the color sort of mapping is a proprietary defined curve of a vendor's versus a sort of standard linear transformation in between colors. So I think this is a natural evolution, but having the standards in place where those from a full stack standpoint can start adopting them to have the most accurate and reproducible visual representation is where we need to go.
Yeah, I think this is just emphasizing that part, right? This is, I think, where some of the other standards, for example, for just storing pixel data also fall short, because here the domain where we use the images is really medical diagnostics. So, while normally if you just look at, a photograph on the internet, whether the color is now perfectly reproducible may not matter. But if you look at a histopathology slide that was stained with a very specific stain, where color actually provides the contrast that may be necessary to see a certain feature for diagnostic purposes, that all of a sudden may be very relevant, and not having that reproducible may lead to diagnostic inaccuracies and so forth. And I think that is the mindset also that DICOM brings in, even though there may be some gaps now still for other modalities, like newer modalities. But realizing that some of these things like, grayscale and color representation need to be accounted for is probably the most important part here to emphasize.
So I know we're slightly deviating from I guess we aren't deviating from the talk track, but Markus, from a clinical standpoint, could you maybe comment on how sort of the multispectral acquisition space is, complementing the different variations in color and how they can be used in this domain?
What do you mean exactly?
DICOM would usually be acquired in sort of a single view imaging data, but I've seen a lot of more advanced sort of microscopy acquisitions from a hardware standpoint, being able to have many, many different color components to them beyond just RGB, so that you can actually move between different color components in the acquisition to be able to see different views of the specimen. And I've seen that being used quite a bit in microscopy within the domain, which seems to be another sort of, improvement upon the domain in DICOM. I was just wondering on your view of using that from the clinical domain.
It's a great point, and it's something I've worked on a lot in the research space and have been working on with multiplex immunofluorescence imaging, for example. There now actually the two worlds collide and meet each other, because there the data is also stored as grayscale data under the hood. It's usually not displayed to the user as grayscale data, but you pseudo color it for display. And you may potentially blend multiple different grayscale values into a color representation where you color one channel red and the other channel blue and the next channel green, and then bring all of them together to form kind of like a pseudo RGB image. Now here you basically need both, right? You first need to deal with the grayscale values, because they're also, for example, the images may be acquired and stored as like 16-bit integers, unsigned integers, but then the dynamic range is only from, 100 to like 500. And so a lot of the actual dynamic range of the underlying storage format is not utilized. You need to window the images and so forth. So all of the things that we talked about in radiology, if you would now display these grayscale values, the same problems exist similar to a CT image, right? Where you may interpret high intensity values differently than low intensity values. If you now color code them, you also have this problem that, for example, depending on the wavelength of the color, we may perceive intensities very different. There are differences between the blue and the green colors, and if we now blend them together, that also creates all sorts of complexity. DICOM is able to deal with all of that. You have, modality lookup tables, presentation lookup tables, all of these things, palette color lookup tables to specify a certain color map for mapping the grayscale values into color values and so forth. Now, whether somebody's using that is a different question. But I think as we move with some of these applications now from a research setting, where a lot of that probably was just ignored, into clinical practice, some of that may become very relevant, and we should start thinking about this. And this is, I think, where a lot of the research formats ultimately fall short, simply because they haven't really considered that when designing the format, and now bringing that in at a later point is much harder than just accounting for it in the first place and realizing that there's quite some complexity in getting the stored pixel values into something that you can display on a monitor to a clinician so that the clinician can interpret that data reliably in clinical context.
Thank you both. That's very enlightening. I've definitely learned a lot just from that last question. It's quite eye-opening from somebody who's consumed with radiology images and, black and white images, so to speak, to learn about all the nuances involved. Now, that being said, I do want to take another stab at technical standards, if you don't mind. So my eyes have actually caught mentions of an IHE standard here called Digital Pathology Workflow Image Acquisition. The shorthand form is DPIA. Would you gentlemen give a quick introduction to the profile here and what it does?
Yeah, so this profile comes from integrating the healthcare enterprise, or IHE, pathology and laboratory medicine domain. So that's the PALM domain of the IHE. So I think a lot of people in the radiology space are also very familiar with IHE. So what IHE does is it formulates certain profiles within a domain. So here in the pathology domain, that would basically now standardize workflows. And so the IHE is different from DICOM, for example. It's not a standard setting organization, but they basically define profiles on how you use standards and maybe other things to ultimately implement a workflow clinically in a standardized fashion. And so what the DPIA does, that stands for Digital Pathology Image Acquisition. It's basically one profile in the entire digital pathology workflow. And so for that profile, the workflow has been considered to really start with ordering, where, for example, a surgeon may have collected a specimen from a patient and might now send this to pathology, basically implicitly requesting the analysis of that specimen, all of the things that happen in the pathology side of things, to ultimately the issuing of a report that is being sent back to the clinician that would provide the diagnosis or description of that specimen. And so various profiles have been defined, at least conceptually or outlined, that would cover that entire workflow, from the ordering to the specimen preparation, the digital image acquisition, and that's a DPIA profile, to the point of where you, create certain evidence on the images, like you would run an image analysis program, for example, you would get results back or an image annotation. How do you report that ultimately back to the clinician? So the DPIA is that part that deals with the ordering, the acquisition, the storage, and the display of digital imagings. And what's really important here, and that's something I've touched upon earlier with the specimen module that was introduced into DICOM, we have the ability in DICOM to store metadata about the specimen in the DICOM image data set. But the question is really, where do we get that useful information from? And so that's the area where the imaging systems, in order to incorporate that information into DICOM, need to get that from the laboratory information system and maybe also from the electronic health record. And that interface, how EHR, LIS, and imaging systems interface with each other or communicate with each other, that is basically the part that the IHE profile tries to cover. Now, what's exciting is that the DPIA relies on DICOM for everything that's related to image storage and image display. A standard called DICOM Web, which is basically DICOM on HTTP protocol, is being utilized here. So the whole interaction between viewer and PACS is basically based on DICOM Web. But the profile also introduces some additional messages that would allow the LIS, or the system requesting the imaging to be performed, to communicate information about the patient and the specimen and so forth with the image acquisition device, so that this information can be incorporated into the DICOM header and can then be utilized by imaging systems without those imaging systems always having to go back and ask the EHR or the LIS for certain information. So it's a very critical step in the entire imaging workflow. And it's something that we have struggled with for quite some time, to get LIS vendors to talk to imaging system vendors to figure out how that information can basically be shared across these system boundaries. I think similar profiles probably exist on the radiology side. I'm not that familiar with those.
Yes.
Between the RIS and the PACS and all of that. So
yeah. So one thing I can contribute here is to say that, again, on the digital pathology side, it seems like this is a evolutionary thing with a lot of templates in place for radiology, cardiology, existing sort of imagingologies. I love the approach that IHE takes in being able to say, this is the decoupled architecture between different actors in the system. These are the messages that need to be exchanged to promote the workflow. So I think this is, again, just a natural evolution for the digital pathology space to have this represented, where existing sort of clinical application vendors can start knowing better from a interface standpoint where they need to make sure that they have the proper abstractions.
Yeah, so it sounds like the DPIA profile is kind of like the mother of all profiles as far as digital pathology is concerned, which is great, because the analogy here would be on the radiology side, you have the SWF profile, which is the scheduled workflow. That's often referenced as like the mother of all profiles, or like the fundamental one in radiology. Now, gentlemen, I want to take a quick detour because Markus happened to mention the report. And that kind of sparked a thought in my mind of, if you don't mind, very quickly, what does the pathology report look like? Is it anything similar to radiology report? Do you use similar tools for things like voice recognition? Anything for our listeners to understand about pathology reports would be appreciated.
So there is, maybe just to recognize at that point, most of clinical practice is currently not digital in pathology. So pathologists primarily review glass slides and then record that information and describe basically the specimens in a report. So the report is typically broken down into various sections where some parts of the report also describe the gross specimens or the surgical specimens before they were sectioned into slices and then stained and looked under the microscope. So there's the macroscopic examination of those. And then there is the microscopic examination, usually then concluding with a specific diagnosis. But what's different maybe also from radiology, although I think in radiology it's similar, that none of the reports are actually imaging centric at the moment. They usually operate at the case level or in radiology, the study level. So a lot of the information is not, in this particular image, we found this and that. It's more about certain features were found in the case and they may then occur in one of these images. And I think that's one of the major changes that will probably happen with the increased digitization and also AI taking over, that we now detect things in particular images and we may want to report that this has been found in this image, maybe in this location in the image and so forth. But at the moment, it's very case-centric and it happens through the LIS typically, where pathologists either dictate it and then it gets typed and there's voice recognition software. There are various systems that all depends on the laboratory information system. I think similarly to how it depends very much onto the exact implementation of the RIS in radiology.
That is really interesting. And for the record, because you mentioned the report and findings from specific images, so there is a new IHE profile being worked on as we speak right now called interactive multimedia reporting, which is kind of trying to take the things in that same direction you're talking about, that make the report a bit more image-centric rather than general in nature. It would be interesting to see if maybe any gains on the radiology front here can translate to gains on the digital pathology front.
I hope the pathologists are taking notice.
I hope so too. And then after we record the episode, I'll happily put you in touch with some of the people working on that profile, because at the very least, it might be worthwhile that whatever they're designing may not necessarily design for pathology, but at least does not design against pathology, if you know what I mean.
Yeah.
Excellent. Now, you mentioned AI, and I want to come back to it, but very quickly, I want to ask a question, because we recently had an episode on this podcast where we interviewed a couple of clinicians from the Digital Pathology Association, and we asked them questions like, what's the current state of digital pathology in real life right now? I would love to hear your perspective on things, considering that you gentlemen are a lot more immersed in the technology side of things. So if you don't mind telling us what it's like right now in real life, and what's the status of things like telepathology?
Yeah, I think from a clinical perspective, most of clinical practice is not digital at the moment. So most of the sign-out actually happens on glass slides. So from that perspective, digital pathology is still very much kind of like a research and education tool. That is changing a little bit, but there are some, fundamental difficulties that need to be overcome to incentivize institutions to go digital. The major difference here to radiology is really that by implementing digital pathology, we incur additional costs rather than saving costs. So in radiology, most of the image acquisition systems were actually digital to begin with, right? A CT generates a digital image, and those were printed on film. So there was a lot of overhead in generating the film, moving the film, and so forth. In pathology, it's the opposite. We start with a glass slide, and we still have a slide, and now we digitize it. Now we have a digital copy of that slide that we also now need to pay for. We need to store it somewhere. We need to move it. So there are a lot of additional investments necessary for digital pathology. And at the moment, the major question is is that investment worth it? And so I think we'll see where this goes. There are definitely some use cases, I think, where digital pathology could be really useful. It would allow you to basically practice pathology in a different fashion. You could decouple, for example, the generation and preparation of the specimens from the interpretation of the images. They don't necessarily have to happen in the same laboratory and so forth. Whether that incentive is strong enough to actually move the whole field digital, I think we'll have to see. And one other force that you've already mentioned is, of course, AI. So I think a lot of the revived interest into digital pathology, which is essentially already around for a couple of decades now almost, from a technology perspective, it has matured, but the adoption is still pending. And so at the moment, I think everyone is excited because we see now these huge advancements in AI, also in radiology, right? And the hope is that these new technologies can be applied to pathology as well. But of course, that will only be possible if we digitize the image. So the incentive for digitizing may come now with the ability to then analyze the images and go just beyond viewing them on a monitor remotely.
Yeah, so I'd like to contribute a little bit to that as well. As Markus was saying, looking at many slides from a sort of retrospective standpoint, I can't think of any more useful way than through digitization, because of the fact that you could have, GPU or CPU accelerated analysis of many different imaging assets. I mean, even just looking at a single slide, not that it's easy from a classic radiology side to detect a finding within a image, but you multiply that many times with respect to the sort of scope of what you're looking for when you look at a single digitized pathology slide. And naturally, you could see that having computational improvements around that is going to affect efficiency. But again, just as Markus was saying, I think the domain is evolving. It is moving maybe slowly toward the digitization. I mean, naturally, as with everything else, COVID, kind of, I think, moved in that direction in some ways. Yeah, we're going to see, how it goes. I mean, I think AI, decoupling the pathologist from having to be in a single location where you're only working off of a single microscope in sort of the telepathology realm. Same with radiology, where you have teleradiology. I think that makes sense in some ways from a business standpoint. So we will see.
Thank you. So maybe we can cover a topic really quickly. I'm sure digital pathology is also enjoying a healthy dose of AI hype and maybe some truth. Can you cover what AI is like in digital pathology right now?
Yeah, I think we're lagging behind radiology maybe by a couple of years, simply because of the fact that in pathology, not a lot of data is currently digitized. Radiology is looking back at like 20 years worth of digital data. In pathology, we're still struggling in like digitizing slides in the first place. So that's why I think there's a little bit of a lag. But recently, the first algorithm has also been cleared by the FDA. And so I think that hype is now also basically will get to its peak sometime soon. Yeah, I think the interesting part in pathology is that we basically have these two almost conflicting things. On the one hand side, we're not fully moving digital. On the other hand, we want to use AI. So now the question is like, how are we going to incorporate AI into a workflow that's not even digital yet? I think it also offers a couple of opportunities because we can get a couple of things right that I think radiology maybe didn't do in the most optimal fashion, because some of the workflows were designed 20 years ago when AI was not really a thing. So I think all of what we talked about earlier, the DPIA and the integration of information from the laboratory into imaging data or linking it with imaging data, or at the same time, like how do we then take imaging data and report it back to clinicians? That is something I think pathology can now take a very different approach from the initial steps in radiology and get some of the things kind of like immediately right for AI, where we now have the opportunity that we don't have a lot of legacy systems currently in place yet.
I 100% agree. Yeah, I mean, radiology has had a sort of long track here. So learn from what was done, be able to build on top of it, but try to, hyper optimize based on the current needs and the current tools that we have, right? I mean, AI is incredibly useful in many ways. So trying to apply it to the modern sort of representation of imaging within the digital pathology space, I think that absolutely makes sense. Yes.
That's something that we're currently trying to move forward, where I think the current situation is also that we have a lot of startups or companies that are now starting to offer algorithms either in the research space or already now moving into clinical space. But at the moment, if you look at these offerings, they would typically be, well, in order to use the algorithm, you also need to buy our storage system, and you also need to get our dedicated viewer that then allows you to visualize the algorithm results and so forth. And this may be manageable with one system, but I think if this hype is now really moving forward and we're starting to see more and more algorithms becoming useful clinically, it will probably not be feasible to have 15 different storage systems for 15 algorithms and corresponding viewers. We probably want to have like one viewer where pathologists can consume that data from, and these different algorithms integrating with that. And so now that is a major challenge at the moment for the entire field and how we're going to do this. There is the problem in digital pathology even that the FDA initially approved whole slide imaging systems along the entire pixel pathway, meaning the scanner, the storage system, and the display system as one box. And we're trying to break that up. And now AI is another vector in there that makes these things much more challenging. What if I have a display system from this vendor, but I want to display the results from that AI vendor and so forth? This is where we are currently very actively working on in DICOM Working Group 26, as well as in the DPA Standards Working Group. We've been starting to conduct so-called hackathons where we're trying to bring the different stakeholders together, different vendors that offer display systems, storage systems, algorithms, and so forth, and try to communicate both the imaging data to bring it to the algorithm to run some analysis on, but then also take the results that are being generated by the analysis and integrate them back into a workflow where they can be displayed on a monitor. So it goes way beyond just like displaying the images themselves after they've been acquired, but now we have basically certain artifacts that were generated by analysis, like a segmentation, certain objects that were detected, measurements that were taken for each detected object, and so forth. And how can we do this using DICOM, using a standard workflow, and basically making a lot of different components interoperable with each other?
This is quite honestly a soapbox that I'm on whenever I speak to people about medical imaging and AI. I mean, as Markus was stating, there are a lot of current AI vendors out there who are really just trying to perform a certain function, which means they're going to, quite honestly, implement the full stack in their own kind of proprietary way and deliver that function to the organization. But the main issue I see is it really doesn't foster any innovation externally, which is why, quite honestly, from the interoperability standpoint, using DICOM as the primitive to be able to acquire AI results, consume, input to models when they're being created, this is really what fosters innovation, which is where I absolutely see the standards playing a huge role in AI. If you look at the IHE AI workflow, I would reference that and take it to the extent to say that, all objects should really be DICOM within the medical imaging domain for AI as well.
Yeah. So we talked a lot about grayscale values and how they need to be adjusted so that humans can interpret them reliably, take into account basically the human vision system and how that works. I mean, all of that even more so applies now to AI results. Like, for example, it starts with simple things like what image was that AI algorithm created for, or what image was it derived from? What specimen is actually being displayed here? If you have a segmentation of something, what is being segmented? Is that tissue? Is that a tumor? If it's a tumor, what type of tumor? And so forth. So, just putting that into some JSON and saying tumor, that may not be enough for a clinician to ultimately interpret that in clinical context. So I think all of the things that we've talked about pixel data now similarly apply, or even more so apply, to image annotations and image analysis results, where we not just need the segmentation mask as, a bit plane, or the spatial coordinates of an object that was detected, like the contour of a nuclei or something, but we need to say that it is a nuclei. We may want to say that this is a lymphocyte or a tumor cell, etc. We may have certain measurements for those. All of that information needs to be encoded in a way so that a recipient, be it a human or maybe another device, right? That's, I think, the future that we want to move to, can read that information and can interpret it so that the information can be used in context appropriately. I think without a standard in place, a lot of that will be very difficult to impossible. And what we figured out through this hackathon is that a lot of these mechanisms already exist in DICOM. They were not designed primarily for AI, but for other image annotation and image analysis tasks. And they can readily be used to support AI workflow. So that's a development that I think Jason and I are both very excited about and that we're trying to push forward.
Yeah, indeed. That sounds really interesting. I would have loved to ask a lot more questions about the hackathon, but we're very quickly running out of time. So I want to switch to one last quick topic and not waste too much more of your time, gentlemen. Markus, you and your team at MassGen have been working on some pretty cool open source projects, things like the Slim Viewer for Pathology, DICOM Web Python client, DCMJS library. Would love to hear more about that from you and Jason.
Yeah, thanks for bringing this up. What I just talked about in answering the earlier question is exactly that, right? What we are trying to do is do all of the image analysis and image annotation and everything in DICOM. In implementing that, we've developed a lot of tools to facilitate it. For example, for a Python or a JavaScript client to interact with a DICOM web server over HTTP protocol. Or, so that is, for example, we have a DICOM web client implemented in Python and a DICOM web client implemented in JavaScript that can run in the browser. Or if you have image analysis results that are generated, for example, with, the TensorFlow library or PyTorch or something, how do you get that into DICOM? So we've created a library called HiDICOM that makes it basically NumPy plus some metadata, and then you have a DICOM object that you can work with and that you can display. And lastly, the Slim Viewer, which is now an image display system that is very lightweight, that just runs into your browser, and it has no backend, no server component other than DICOM Web. You can basically put it in front of any PACS. It will detect any slide microscopy images and corresponding annotations, segmentations, etc. We'll pull that out and we'll display that to a user solely based on DICOM standard. So once you have a system, like for example, the Google Healthcare API, right, which provides a DICOM Web system, you can just put that viewer in front of it, authenticate with OpenID Connect or OAuth 2. And then once you're authorized to access it, you can just view all of the data in your PAC through a web interface. And so we hope that a lot of these tools will also enable other people out there to adopt DICOM for their digital imaging workflows, in particular for AI and machine learning applications, where currently there's not a lot out there to encode that information, particularly in languages like Python and JavaScript that are being used either on the server side to generate that data or then client side to visualize that data to use it through web page, basically.
Yeah, and I just want to call out and thank Markus and his team for promoting these tools and for promoting the standards within this domain. Just looking at things like HiDICOM and Slim Viewer more as kind of your application from a visualization standpoint for digital pathology. I mean, these sort of assets, open source, can be consumed by anyone and really get them up and running in quite a complex domain, I would say. And just being able to produce, SR objects from, large scale imaging, that's incredibly helpful to have a tool that can get you up and running via that route. So yeah, I just want to, again, thank Markus and his team for really pushing that forward.
Thanks. And maybe just to mention, right, apart from the Slim Viewer, which is really designed for slide microscopy images, a lot of the other tools that we've developed, the DICOM web client, HiDICOM, and so forth, they are really not pathology specific. So actually, we use them for radiology with CT images and MR images and so forth. So these are really tools, I hope, that will help us get to more kind of like an integrated diagnostic workflow where we perform image analysis and annotation independent of its exact modality, and we can encode the results from a CT image analysis very similar to the results of a slide microscopy image analysis workflow, and basically put that all into the same PACS and now have different viewers, Slim for pathology or like OHIP, for example, for radiology, that work and use some of the same libraries under the hood on the JavaScript side to then basically do this fully integrated with one PACS backend, independent of whether that's pathology or radiology domain specific.
Yeah, absolutely. And I should mention, I've definitely used some of your tools for radiology purposes. And I know of other good friends like Chris Hafey who use some of these tools. So yeah, kudos to you and your team for this work. Gentlemen, I really want to thank you a lot for your time today. It's an extremely interesting conversation. I feel like we're probably going to have you soon to talk about some of these things in more details. But for today, I highly appreciate your time. And I hope everybody who's listening to this episode enjoyed listening as much as we did.
Simcast has been brought to you by the Society of Imaging Informatics in Medicine. Please visit our website at siim.org for more information and educational content, including webinars and an archive of prior episodes. Please follow us on Twitter at sim_tweets. Thank you to our listeners for your continued support.